So thank you. This video that I have been showing here, it's just a brief example of what we have been doing in the reconstruction of the virtual reality moon. So if I can start, yeah. So maybe you are wondering why we did this project on virtual reality for the moon. So this project comes or follows another research project by Eric Kulkers and Time-Lab Technologies on the investigation of the X-ray spectrometer that was on board the Apollo 15. And for the proper interpretation of some of the X-ray data, we needed to reconstruct part of the mission that at least we couldn't find it public. So we did a lot of reconstruction. And once we had all the products of that reconstruction, we realized that these assets were quite nice for doing something on virtual reality on the moon, something that can be used for future projects or future missions. So this is why we did all this after the project. And once I start showing things, you will realize how this works. So let's see. Yeah. So a brief summary of what I will talk about. Of course, first a brief summary on Apollo 15. So it was the first scientific mission on the Apollo program. So that's why there's a lot of stuff there. Then something on the data that we use for the mission, and also which data we had to reconstruct to have the full picture. Once we had all this data, we had to reconstruct or recreate these scenes. So this means the 3D assets, so basically 3D models and the terrain. So also how we integrate this geometric data of the mission with these 3D assets, and also some physics and some mechanics that we had to implement to provide a more immersive experience for the user. Then once we had all this, we wanted to integrate virtual reality with this experience. So we target first Cardboard, which was the main platform that we want to develop for, but also we adapt all these scenarios for Oculus as well. So I will talk about that at the end of the presentation. And just to finish, I will give some examples of other applications that all these assets that we created in this project, other applications that can be applied. So Apollo 15 mission was launched in 1971. So next year will be the 50th anniversary of this mission. And the most important thing is that it was the first Apollo mission devoted to science. So with this purpose, they spent 7 days on the moon. And this means not only 7 days on the surface, but also 7 days on the lunar orbit doing experiments. Some of these experiments are the X-ray spectrometer, which is the main driver of this investigation, and it's located at the bottom of the scientific bay of the Common Service Module, as you can see here in this picture, which, by the way, is a real picture taken by the astronauts from the lunar module while they were ascending at the end of the lunar phase. So also with this X-ray spectrometer, we have the gamma ray spectrometer, which was quite useful regarding the reconstruction or the geometric reconstruction of the mission. And also, for example, the mapping camera, which took thousands of images of the lunar surface. And these images, we use them for, let's say, improve the attitude that we compute from the telemetry of the previous two instruments. So that's for the orbit, but of course in the surface, as I said, the astronauts did a lot of experiments. For example, you can see in the image on the left, the ion detector, the solar wind spectrometer, magnetometer, seismometer. And in this great image on the right side of the slide, you can see the roving vehicle, which actually they are the first wheels on the moon, the first wheels outside Earth. So quite a great thing for space exploration. So that's the brief summary. And then about the data and documentation, one thing that we realized during all this project is that there are a lot of sources on data for the Apollo 15 mission. It's been almost 50 years. So the data and the sources are also quite scattered. So sometimes it's quite difficult to know where to search some data. So if someone wants to know about Apollo 15, I have put here the two documents that for me are the most relevant. So the first one is the flight plan. So basically it's like this here. So there are hundreds of pages with handwritten annotations by the astronauts, and these annotations are like exact times of some maneuvers or some geometric quantities. So this was quite useful for reconstructing some parts of the mission for example, for the lunar module descent and other parts of the mission. And also the mission report, for me, it's quite interesting because it still is a technical document, but you have a general description of most part of the mission, like all the phases with the times of the phases, the description of all the experiments that they did both in orbit and in the lunar surface. You can find some drawings like these ones of the rover or the surface experiments. And also you have some pictures like this one on the right describing the landing site and the distribution of the experiments in the landing site. So that's about some of the documentation, but of course we need geometric data. And first we reconstructed the orbit because we realized that there was not quite much data on that. There were some data available from the mapping cameras, but of course they were only on the light side of the moon, so we didn't have a full revolution, for example. So what we did, we used the telemetry data from the gamma ray spectrometer that I mentioned before. So in this telemetry, we have positions and velocities with a frequency normally of every 3 seconds, except from these gaps that you can see in the plot below. But these states are quite enough for propagating the orbit, quite simple propagator, including the Earth and the Moon gravitational potentials. So with this, we have the orbit that you can see here. And in this orbit, some of the phases of the mission can be appreciated quite well, like the high altitude phase at the beginning, right after the lunar orbit insertion. Then we can see the low altitude phase, at the beginning of which the lunar module undocking happened. So just to mention here that if you have seen the video of the lunar module descent, it includes only the 10 last minutes of the descent, but 4 hours elapsed between the lunar module undocking and the actual instant of the touchdown on the moon. So for instance, they did 2 revolutions around the moon during this descent, let's say. And also, you can appreciate these 2 inclinations, like the main phases of the lunar stage were at 23 and 25 degrees. So that's for the orbit, but of course we need the attitude for interpreting the X-ray measurements. So this comes from the telemetry of the X-ray spectrometer, actually. So we have local horizontal angles that once we have the positions and velocity, we can interpret these angles in terms of lunar body fixed angles. So with this, we could interpret the X-ray data. But of course, we feel that we wanted to reconstruct the whole attitude or the attitude for the whole lunar mission. And you can see here that there are a lot of gaps. So what we did to fill these gaps was using the mapping camera images. So we create a Python package called SPIREC, which basically simulates the images using the digital terrain models and the illumination angles. So on the left, you can see the real image. On the right, you can see the simulated one for the same instant. And you can appreciate some offset between this image. So what the SPIREC does, it's compare these both images like as binary images. So comparing pixel by pixel, it's introducing an optimization process. And this displacement on the simulated image can be related to a quaternion of correction, let's say. So what we did was creating all these corrections for all the pictures that we have from the mapping camera. And in this way, we improve even a bit better the attitude that we have from the X-ray spectrometer telemetry. So that's for the command and service module. But of course, we want to land on the moon. So we wanted to reconstruct also the trajectory of the lunar module. But sadly, we couldn't find any data or any actual data on the Apollo 15 lunar module descent. So what we did was we took a standard profile of the descent for the Apollo program. So in this profile, we have the altitude profile and pitch profile. So we took the final landing site of the lunar module that has been computed with quite high accuracy using lunar reconnaissance orbiter images. So I will show in the next slide which image I'm talking about. And we create a standard profile, which of course is not the exact one that Apollo 15 did, but we think it's quite enough for transmitting the experience or the feeling to the user in a virtual reality application. So this image on the left is the one I was talking about from the Lunar Reconnaissance Orbiter. And in this great image, you can appreciate the ALSIP, which was the place where they did all the experiments, but you can appreciate also all the markings of the wheels on the lunar surface, the wheels of the rover, of course, which you can see it on the right of the image, and you can even appreciate the wheels of the rover. So this is quite a nice image that we use for reconstructing more or less the distribution of the experiments and the rest of the objects in the landing site. And the image that you can see on the right is the real image that the astronauts took from the lunar module. This was just a few moments before landing. And this image, we use it to reconstruct, it was provided by someone who watched the videos that we did. And we use this image to reconstruct, or let's say to improve the heading of this descent trajectory that at the beginning was not the correct one. But with this image, we could demonstrate, we could prove that the lunar module was coming above the mountains to the rail and not from the other side as we had at the beginning. So that's for the spacecraft trajectories, but of course we need a moon to land on. So for the moon, we have used two approaches depending on the scene that we are talking about. So we are far from the surface, like orbiting the moon. We use a global model from the Lunar Reconnaissance Orbiter cameras and the altimeter for the terrain. So what we did is use a plane sphere in which we project the albedo of the moon and the normal of the moon, which basically it's the vector normal to the surface at every location on the moon. So I will show you in a minute how we use this. Basically, this is for saving performance because we want to run this on mobile phones. So performance, it's one of the main drivers of all this implementation. So that's why we're not using a global 3D model of the moon for these orbiting scenes. And for the scenes in which we are close to the surface, like for example, the lunar module descent, and of course the landing site scenes, we use regional terrain models, so basically meshes, which are computed again from the Lunar Reconnaissance Orbiter altimeter global products. But in this case, we are taking just some regions. So in this image at the bottom right, you can see how both things can be implemented together. In this case is the moon that we use for the lunar module descent. So for the regions close to the landing site, which is more or less at the center of the image, we have a 3D model for the terrain. But for the far areas of the moon, we have this albedo plus normal 2D model of the moon. So this is just an example for those who doesn't know a lot on 3D rendering, like it was my case 1 year ago. So this is an example of a plane sphere. So it's a sphere without any alteration in the mesh, but we have used a normal map to recreate the 3D terrain on the surface of the sphere, just affecting how the light is reflected or how, let's say, the incident angles on the surface of the sphere. In this case, just to mention, it's a normal map from the Mercury terrain model. So this is just to give a taste on the effect of the normal map. So we have the moon, but now, of course, we need some spacecraft to orbit and to land on the moon. So for the command module, we have used this amazing model from the Apollo 11 command module done by Smithsonian. So of course, it's not the same exact one command module that they had in Apollo 15, but the main difference was one panel that they had for controlling the experiments in the scientific bay. But again, I think for transmitting the experience to the user, it's quite enough. So for the lunar module, we have this simple model here that we use for landing on the moon. And we have also this model for the roving vehicle, because as you will see, there's one scene and you can actually drive the rover on the lunar surface on the actual landing site. So together with the spacecraft, we have some models of the experiments that you have on the lunar surface. So we had to reconstruct all these 3D models, and we did this based on the image. So on the top row, you see the real instruments, and in the row below, you can see the reconstruction, or the, say, the interpretation that we have from these models. So just summarizing a bit on how we integrate the data with all these 3D assets in the model of the spacecraft and on the moon. So we use SPICE. We use SPICE kernels integrated with Unity, which is the software that we use for creating all these 3D and virtual reality scenes. So we take positions and attitude for the command service module and lunar module using these SPICE kernels. And for the moon, as I said, we use these lunar reconnaissance orbiter datasets. And again, for the lunar module and surface experiment, we took positions based on the images, both from the mission report and from the lunar reconnaissance orbiter images. So then to show the final results for those who haven't seen the videos yet. So this is for the command service module orbit. You can see here in the center of the image, the command service module orbiting the moon. So positions and attitude are given from the SPICE kernels. So these are the exact geometry that we computed for the lunar phase. And the moon, in this case, is modeled with this albedo plus normal. So as you can see, it's quite difficult to say that this is a 2D model of the moon and not a 3D terrain. So this is the result of using this albedo plus normal. And on the right, you can see the image from the inside of the command service module, which is what you can see from the virtual reality applications. And this is what the astronauts were actually looking at while orbiting the moon in the Apollo 15 mission. So for the lunar module descent, again, we introduced the geometry in SPICE kernels, so SPK for position and FK and CK for the attitude. And you can see here the descent profile. So indeed, they were coming above the mountains, quite close to the mountains actually, and they were landing quite close to the Hadley rail here. And here you can see this image on the right, which tries to reproduce the image that I saw before that the astronauts took while they were above the Apennines before landing. So just to mention that in this case, of course, the moon, it's a 3D model, it's a 3D mesh, and in this case, it's 28 million triangles. So you can imagine that this is quite a big model, but still something that can be handleable for the mobiles that we have nowadays. Actually, we have tried it in several mobile phones and they can run it perfectly. So for the landing site, so the spacecraft landed in this region that you can see here. And in this image on the right, you can see more or less the distribution that we reproduce with the experiments above then the lunar module and the roving vehicle. So of course, you maybe have noticed that the distance are quite smaller here that they were actually in reality. But this is basically a trade-off because we didn't want the user to spend 2 hours walking with the virtual reality glasses on to go from the lunar module to the experiments and then go back to the rover. So of course, it's not the reality, but we think it's a good trade-off between historic accuracy and providing, again, a good experience to the user, which is one of the main points of this project. So just to finish, we have physics and mechanics because we want the user to be able to interact with the landing site. So basically we did this by creating a body for the user. So it's what it's called a capsule collider with a camera for simulating the ice. And in order to interact with the cardboard, for instance, because with the Google Cardboard, as I will talk in a minute, you don't have any controllers in principle, you don't have hands. So the only way that you can interact with things is with a reticle. So basically you have a point and you point with this to any object. And in this image here, for example, you can see how you can get information on the lunar module. And this is a way of having something like, let's say, like a museum on the lunar surface. So you can approach to some objects on the surface and you can get information on the experiments or on the roving vehicle and so on. And of course, we want also to have collisions and materials like to reproduce how they collide between them, because it's not the same to collide with the lunar module or with the surface of the moon. And of course, at the right, you can see how all this is implemented with the roving vehicle. So we have some colliders for the wheels, some colliders for the rest of the structure, but this goes much further because we can tune all the parameters of the vehicle, like the engine force, the torque, the maximum speed. We can tune the brakes, the maximum brake force, the friction of the wheels with the surface. We can tune the suspension. So as you can imagine, this can be applied to any other mission. And you will see later that this can be translated easily to other missions, like, for example, the ExoMars Rover. So this is, again, one example of how all these assets that we created with this project can be implemented easily to future missions. So about the virtual reality integration, Cardboard was the main platform that we want to target for. And this decision was basically because everyone can have a Cardboard with 20 euros or even less. You can have a headset like this one that you can see here. So you just need your mobile phone and the Cardboard, and you can experience virtual reality. Of course, you have some drawbacks because basically the hardware limitations are the ones of your mobile phone. So you have a resolution limitation and a frame rate limitation. So basically this translates into more fatigue for the user. So you cannot use this virtual reality for too long because maybe it's not quite healthy for the user. But again, the great thing on Cardboard is that you can have, for example, a classroom with 100 students all playing around in the same virtual reality moon, or for example, in a virtual reality class that maybe for the times that we have now, it could have been quite useful for the last months. So Cardboard is one example that you can all experience with the project that I will put a link at the end of the presentation, so you can download all these applications and you can experience them. But we target also Oculus, which is like the expensive cousin of Cardboard. So Oculus is this device that you can see here on the top right. So you don't have only the headset with Cardboard, but you have also controllers in your hands. And basically these controllers say they reproduce exactly your hands. So you can interact with every object of the scene, like grabbing objects, throwing objects. You can play golf in the moon, like Apollo 17 astronauts did. So the possibilities are infinite. And this can be implemented in many other missions as well. So quite nice asset to have to be translated to other missions. And just to give some taste of my experience, my brief experience with virtual reality, the next generation headset will allow us to have more powerful hardware. So this will mean that we will have more complex procedures or more complex scenes. So for example, you will be able to reproduce a whole mission. So for training astronauts, for instance, it's quite a nice asset to have. So this is a fun example of what we can do with this Oculus. So basically it's me reproducing the hammer and feather experiment that the Apollo 15 astronauts did. So you can see on the right video, the real experiment. So they drop a hammer and the feather on the moon, and they prove that in vacuum they should fall at the same time. So we can reproduce all this with Oculus because we have the same physical conditions in our moon than in the real one. So they fall at the same time. So this is, again, just a brief example, a fun example of everything that we can do with all these virtual reality scenes. So not only for Apollo 15, of course, if we have created all these models or these assets of the moon, we can easily apply this for Smart 1. So you can see in this image, and you can play around also with the virtual reality applications that we created. So you can orbit the moon with a Smart 1, and we can, for example, render in real time the images taken by Amy. And we can see these images in this small screen here. But for example, we can also project on the surface of the moon the geological data or the X-ray spectrometer data, and the scientists can visualize all this in virtual reality, play around with all this data with his own hands. So maybe in the near future, this is not such a futuristic idea. And this image on the right shows a brief implementation of a more imaginative rover that may happen in the next year for the moon. And also this, again, you will see in some seconds a video in which you will see how all these assets are applied for the ExoMars rover, which was done with a minimal effort once we have all these assets from the project. So just to finish, a brief video of some of the applications. So this is the roving vehicle which you can drive, and you can download this application in your Android phone, and you can play around with it. Like quite a wide region of the moon, not only the lander site is modeled, so maybe you can drive the rover for 20 minutes. So this is again the other rover design that we can apply exactly the same assets can be applied directly to this model. And this is again the same application, but for the ExoMars rover. So you can see that the number of wheels, it's not even a limitation. And again, we can also tune the engine force, the torque, and we can use all this to create an arbitrary trajectory on a real DTM of the landing site, or one possible landing site for the ExoMars rover. And then we can investigate all this trajectory with rendering the images of the PanCam or any other thing. So everything can be done with these 3D models. And this is just, again, this is just an example of everything we can do and everything that can be done with the assets, which will be public likely very soon. And you can play around with all this. So thanks again. And here you have all the links. So the Git project, and you can download this application and the assets of Unity to play around with it, and also the article of in ESA, in which they explain a bit more all this project. And also, just to finish, a link to the ESA Spy Service channel, in which you can see other applications, like for example a virtual reality descent of Philae, or also the Bepi Colombo flyby, actually. And that's all. Thank you for your attention.